Hi, I'm Matthew McGilvary, and this is our presentation. The Simplex algorithm was developed by George Dantzig in the late 1940s while I was working for the Air Force. World War II had shown that solving logistical problems was helpful in the war effort, and that's how he came to discover the Simplex algorithm. So the Simplex algorithm is so-called the algorithm that runs the world. And here are some examples of the simplex algorithm. Essentially, the simplex algorithm is used when you have a finite number of resources and you want to allocate them in the most efficient way possible. So how it applies in your everyday life is in international shipping and manufacturing, the products which are produced and shipped are decided using the simplex algorithm. So an example of how the simplex algorithm works is if you had 70 people and you need to assign them 70 different jobs, how would you do that? If you just tried every combination, you'd get this number, 70 factorial, which does not lend itself to computability. However, if you can make two simplifying assumptions, one being that you have an objective function to be maximized, like you want to make as much money as possible, and you can break the problem down into a system of linear inequalities, which just means the problem could be represented by a geometric object known as a polytope, then you could use the simplex algorithm to solve it much faster, which can be visualized as walking along these edges and vertices until you reach the highest point of the objective function or make the most money possible. So it doesn't just do this blindly. It has to use a pivot rule to determine where to move along the polytope. So in our project, we use Dantzig's rule, the greatest increase rule, and Bland's rule. And here we visually illustrate the difference between Dantzig's rule and the greatest increase rule. If we imagine this plane is the objective function, Dantzig's rule wants to go as fast as as straight up as possible to the top. So it's going to go from this black point to this red vertex. However, the greatest increase wants to make the biggest jump in the objective function per time. So it's going to go to get this green point. So you see that the pivot rule affects how the simplex algorithm traverses the polytope. Now, how we generated our polytopes is we started with a sphere and we had 400 random points for inequalities. Then we deformed the sphere to make ellipsoidal polytopes. Now, obviously, this took a lot of computation. So we're research affiliates with UNC, and we use the long-lived computer cluster for parallel computing. And each one of our examples takes 1 day of CPU time to do, and we need to do 500 computations. So this took 500 CPU days to complete.
Onto the construction of our data. So for each of our polytopes, they all share two unique facets. And from one facet to the other, we have the simplex algorithm path per pivot rule go from one to the other. And at the same time, we look at the vertices crossed by the simplex path and then run the shortest path algorithm there and keep track of that path. For this talk, we only focus on 3D results. Conclusions for the fourth and fifth dimension are not here, but they hold true. The following animation is just to display through the polytopes the paths that they can take, the pivot rules, and from one facet to the other. On to define R stability, it's a measure of a pivot rule's performance, and for a simplex algorithm's path and shortest path, we do comparison here. So we construct a curve where at a certain percent complete of the simplex algorithm, the curve outputs the probability that the length P1 and P2 are equal. So what R stability is telling you is that it's the largest area formed between any two curves in this set H of all of these curves. One may also see that the sensitivity of the average overall performance the simplex algorithm path has to the flattening of a spherical polytope, and thus higher R stability, higher levels of shifting. And thus we see through these three pivot rules that Bland's rule is more uniform and does a smaller R stability, and a higher R stability goes to greatest increase rule where there is much more shifting. And to compare via minor axis, we see that it holds true that for all, that greatest increase will more likely be one-to-one with the shortest path than the other two. On to average Euclidean distance from the center, we see that for all pivot rules that as the minor axis decreases in size, then you're more likely going to be walking across the face or near the center than walking across the rim. However, when you compare them to minor axes, Bland's rule actually, for a smaller minor axis, will be more farther away than close to the center than the other two pivot rules. And lastly, for the simplex path being stuck on the edge, we want to account for this too. So we define a lower bound that a path can be from the center, and we see how many paths are at least this far. And for all pivot rules, we see that as you decrease the minor axis, you're going to, again, be closer to the center or less likely to be walking across the rim. However, for a large enough lower bound that you could be to the center, the Dantzig's rule will have a higher rate of having a large enough distance from the center than the other two. So what you can conclude is that the greatest increase yields the greatest R stability. All rules passed are not on the edge of the polytope. However, Bland's rule becomes the farthest from the center, and for a sufficiently large distance from the center, Dantzig's rule will have the highest probability that it'll stay that far. And for future directions, we'll look at different pivot rules, higher dimensions, more radii, and more inequalities. Thank you.